All right, welcome. In this video, I'm going to be doing the Algebra 2 Unit 11 review. And while this is a good set of problems, and they are pretty similar to some problems that are on the test that you might be unfamiliar with based on the quizzes, I gotta say before I start, you need to go back and look at the quizzes and the notes and the homeworks, because this is not the longest review I've produced. I was looking, and I decided I wasn't going to just like repeat questions that I'd done over and over again on notes, homework, quiz. So like, what value of k makes the function continuous? That was going to be on there, even though it's not on the review. Okay, so set my disclaimer. Let's get to it. Find f of g of x. So 1a, f of g of x, wherever I see x in the formula for f, I'm going to replace it with g of x. So that's 4g of x plus 5. Okay. And then g of x is equal to 1 minus x's absolute value. So I'm going to say 4 times the absolute value of 1 minus x plus 5. That's f of g of x. 1b, f of g of x. Okay, this is like a multiple choice question that I was just a little bit concerned y'all would not know how to get to the right answer choice. So f of g of x, wherever I see x in the formula for f, I'm replacing it with g of x. Okay, had it been g of f of x, I'd gone over here, and wherever I see the x in the formula for g, I'd replace it with f of x. But we're asking for f of g of x. So f of g of x equals 3 over g of x minus 4. And g of x is 5 over 2x. But, answer choice probably isn't going to look like this, right? So what we would need to do is get rid of this denominator. So what we could do is multiply on top and bottom by 2x, really like 2x over 1. And then we would distribute that in, and then the 2x's would cancel. And I'd have 5 times 2x over 2x, well, that would just be 5. Oh, but I should probably multiply the numerator first. 3 times 2x, that's going to be 6x over 5. And then when I multiply the negative 4 times 2x, I'll have negative 8x. So something like this. And this is more like what an answer choice might look like, because, probably the question writers, a lot like me, don't like layers of fractions. So they take up way too much room on the paper, too. So C, f of g of x, would be the square root of x is now g of x plus 2. So I'm going to replace g of x with e to the x. So it's the square root of e to the x plus 2. And there's not anything I can do with it. I can't just take the square root of e to the x and the square root of 2 separately. Square root doesn't work like that. Okay, that's as far as I can go. So that'll be f of g of x. Number 2 says, use the tables to find the values. Okay, that's another thing I didn't put on here. I didn't put any graphs on here where you had to do composition of functions with a graph. But we did that quite a bit on the notes, on the homework, and on the quiz. It seemed like y'all were pretty good with that, so I just did the table. f of 2 okay, well, I need to figure out what f of 2 is first so I can plug that into f. Okay, so f of 2 is 4. So this is f of 4, because I just replaced the f of 2 with 4 because of that. And then f of 4 is equal to 6. B is g of f of 5. So I'm going to need to find f of 5 first and then plug that into g. So f of 5 is 7. So I'll be taking g of 7, and that will be 12. C is f inverse of 6. Okay, not f inverse of x. So when we're confronted with a problem that says f inverse of a number, what we're going to do is we're going to set f of x equal to that number, and we're going to solve for x. Okay, so f of x is equal to 6 right there, and that would be at 4 equals 4, and I can conclude that f inverse of 6 is equal to 4. So yeah, only 2 more. So the next one's going to be g inverse of f of 2. So we got to find out what f of 2 is first. So, okay, f of 2 is 4. So I'm taking g inverse of 4. And so that's going to be like saying, okay, g of x needs to equal 4. And that's x equals 3. So I'd say that this is equal to g inverse of f of 2 is going to equal 3. Okay. And then next one, okay, g inverse of g of 4. Okay, I know right now that's going to be 4. Okay, because the inverse and the original function, they undo each other and leave you with what you had at the beginning. So, okay, on one hand, I'm just going to say, hey, this is 4. But if I'd done g of 4, I'd have gotten 6, and then I've done g inverse of 6, and that would take me right back to 4. That's kind of the whole point of what we're doing here. So that was number 2. Number 3, write a formula for the inverse of f and find the value of f inverse of 1. Like that. All right. So maybe I'll write a few formulas for f inverse, or for the inverse of f. Okay, yeah, f inverse, maybe f inverse of y, f inverse of x equals some inverse function of y. So if I've got y equals x squared plus 9, and I'm trying to solve for x, I'm going to subtract 9. And if I was to take the square root of both sides, I could solve for x on its own, and I would have plus or minus the square root of y minus 9. Okay, that is a formula for the inverse of f. We could also say a formula for the inverse of f is f inverse of y equals plus or minus the square root of y minus 9. Or if we were asked to find f inverse of x, we would just replace y everywhere we saw it in the formula for f inverse of y with an x, and we'd have plus or minus the square root of x minus 9. All right, I'm also asked to find f inverse of 1. Now, you know, on its own, what we would do is we just set this thing equal to 1. But what I was going to point out to you is that what we could do is we could do this either way. We could say f inverse of 1. We could just plug in 1 for x or 1 for y right here, and it's going to be plus or minus the square root of 1 minus 9, which is not a real number. But we could have also approached this the same way that we already have, or that we always have. So f inverse of 1, I guess I'll put a colon there, I'd say x squared plus 9 equals 1, and we would solve for x, right? So that's going to be x squared equals negative 8, and that's going to not return a real solution either. But the thing is in doing that, I'm just kind of redoing all this work that I did over here to find the inverse in the first place. Okay, this is not real. I'd say it doesn't exist, but we know that these square roots do exist. Okay, but in our class, we think of functions as taking in real numbers and giving back real numbers. So to say, you know, f inverse of 1 is the square root of negative 8, which is an imaginary number, that's not going to be a valid answer because it's not part of our original domain. But that discussion is a little bit beyond the scope of Algebra 2, so I'm just going to leave that there. All right. B is 3 log of x minus 2. And so I'm going to go over here. I guess I'm going to solve for y first. So solve for x. So I'm going to divide both sides by 3. And when we see log with no base indicated, we know that means log base 10. And if we want to get rid of a log, we need to do an exponential. So we're going to take 10 to both sides power. I'll have 10 to the y over 3 equaling x minus 2. Because 10 to the log base 10 of a thing is just going to be that thing. That's something we've learned about in this class. And then I could solve for x by adding 2 to both sides. 2 plus 10 to the y over 3. And then if I wanted to, I could say f inverse of x is going to equal 2 plus 10 to the x over 3. Okay, but either of these would be good if it just said write a formula. Any old formula will do. This needs to be this 2 plus 10 to the input over 3. And if I wanted to find f inverse of 1, I'm just going to plug in 1 here. So this is 2 plus 10 to the 1/3. Okay, that would be good enough for me, but if you wanted to say that's 2 plus the cube root of 10, that would be just as good. All right. C is going to be f of x equals 3 to the x minus 4. And I don't know, maybe on this one, I'll just start off with finding f inverse of 1, and then I'll find f inverse of x more generally. So if I want f inverse of 1, I'm going to set 3 to the x minus 4 equal to 1. And now we could take the log with base 3 of both sides, but I don't think that's totally necessary, and I think that would, end up leaving some of y'all confused because of, I put it on the quiz recently, and some of y'all were forgetting how to take the log of 1. Well, the log of 1 with any base is going to be 0 because any number to the 0 is 1. But I think the easier way to solve this one is just look at it with our eyes. 3 to the what power equals 1? That's going to be 3 to the 0 power. So since 3 to the x minus 4 needs to equal 3 to the 0, I know that x is going to equal 4. And so I'll say f inverse of 1 equals 4. But if I'm trying to, write a formula for the inverse, and I've got y equals 3 to the x minus 4, okay, and I want to get at x, and I want to get it down out of an exponent, I'm going to have to use a log. So I'm going to use a log with base 3 because that's the base of my exponential. Log base 3 of y is going to equal log base 3 of 3 to the x minus 4. That'll just be x minus 4. Then I can solve for x, and that'll be my formula for my inverse, and it'll be 4 plus log base 3 of y. Now, I mentioned just a minute ago that the log of 1 with any base is 0, so what we're going to see is when we plug in 1 here, we're going to get x equals 4 the same way we did over there. All right, now d. Okay, this one, I feel like I gave you all the wrong idea about computing the inverse of a rational function because we did some that had linear on top, linear on bottom. I did a couple of these, but I don't think I did it in the most efficient way. So I'm going to show you that now. That's why I put that on the review. So if I've got y equals 3 over x plus 5, I think that f inverse of 1 is going to be another one that we can solve with our eyes. I'm going to say 3 over x plus 5 equals 1. Yes. Okay, we know that 3 over 3 equals 1, so x needs to equal -2. And with this one, okay, if I'm solving for x, what I'm going to do is I'm going to multiply both sides by x plus 5. And then I'm trying to solve for x, so I need to get rid of that y. And I could just divide both sides by y. And I could solve for x by subtracting 5. And I like this technique much better than whatever I'd been showing you before. Okay, so, and multiple choice wise, what if there was an inverse function like that where the answer kind of just looked like that? Okay, I want to prepare you for that. Okay, number 4. Describe any discontinuities of f. So maybe I should first, write kind of like, what's on the menu as far as discontinuities. Let's put that in the top corner. So we've got a jump discontinuity, which would happen, if the function looked like that. That generally comes from a piecewise function, especially in this class. We could have a removable discontinuity, also known as a hole in the graph, but I need you to know about that terminology. Okay, that removable discontinuity is just a hole in the graph where otherwise it would have been continuous. Okay, now this is a removable discontinuity, and if the dot is placed elsewhere, that's still a removable discontinuity. It's a hole in the graph. We see that usually with canceling off stuff on top and bottom of a fraction. But we can also see this with a piecewise defined function if the domain is like all x except for this value, and then x equals that value at something different. That we could have one of those. All right. And and there's another one. There's an infinite discontinuity, which is just a fancy word for a vertical asymptote. So I might say, I usually draw it like that, because that can happen sometimes, like a vertical asymptote. So for A, I'm seeing a fraction, and we can have discontinuities at the zeros of the denominator. So what I need to do with this one is factor. So I'm going to say f of x equals, and I'm going to think about the numerator. What's common to both of these things? I've got a 4 and 2 powers of x. And then I'm left with an x and a plus 2. Divided by, in the bottom, I've got, just x in common to both of those, and I'm left with an x minus 3. Now, I think you can probably see that, one of these powers is going to cancel, but just want to be super explicit about it. 4x times x plus 2 over an x and an x minus 3. I can cancel off one of those x's, so that'll be a hole. So I'll have a removable discontinuity at x equals 0, and a non-removable at x equals 3. Okay, but thinking about what type it is it going to be a jump or an infinite discontinuity? It's going to be an infinite discontinuity, like a vertical asymptote, because it's a 0 of the denominator after canceling all the stuff. We learned about that in the last unit. So I'm going to say vertical asymptote is going to be x equals 3. Okay, so those are my discontinuities of f for part A. B, I've got a piecewise function, so I know that if the pieces don't agree at x equals 3, that's going to cause a jump discontinuity. So I'm going to say, all right, so investigating 3 plus 2, that's going to equal 5. Whereas when I plug in 3 to the bottom piece, 3 squared minus 3, that's 9 minus 3 is 6. Since these aren't the same, I've got x plus 2 when x is less than 3. That's going up to 5. So this hole has coordinates 3, 5. And then it picks up here at 3, 6, and it's in the midst of doing a parabola type behavior. So that's what the graph looks like. So I'm going to say there's a jump discontinuity at x equals 3. Okay, and that's number 4. So number 5, the graph of f is transformed to produce g of x. Describe the transforms from f to g. All right. So for A, g of x equals negative f of x plus 1. Okay, so I'm going to say, all right, the x plus 1 is left by 1. And then the negative on the outside is a vertical reflection, because all the outside ones are vertical transforms, and a negative, that causes a reflection. So this is going to be a reflection vertically, reflection across the x-axis. B. Okay, I've got 1/4 of f of negative x. Okay. On the inside, that's going to be a horizontal transform. So I'm thinking about over here. If I did a horizontal reflection, that would be a reflection across the y-axis. Reflect across y-axis. And then the 1/4 on the outside, a multiplier is a stretch. And with the vertical transforms, which is what I'm saying because it's on the outside, it works the way we expect. So it's going to be a stretch by a factor of 1/4, or a compression by a factor of 1/4, however you want to call it. But we do need to say it's a vertical stretch. So we're going to stretch vertically by a factor of 1/4. Oh, there's more. All right. So with C, okay, 1/4 multiplied on the inside, those horizontal transforms, they work the opposite of the way we expect. So multiplying by 1/4 makes the function get wider horizontally. So it's going to be a horizontal stretch by a factor of 4. And then subtract 5 is a shift down 5. Next one is 2f of x minus 3. All right, so the x minus 3 is going to be right by 3. And the 2 is going to be a vertical stretch by a factor of 2. And I think I've got enough room to one more here. F of x minus 5 plus 5. That's probably the most realistic transform that a person would actually have to do in a later math class. But that will move your graph of f right by 5 and up by 5 to get to g. Okay, so I'm going to say right by 5 because we replaced x with x minus 5. Okay. Shifts you right by 5. And then adding 5 on the outside shifts everything up by 5 as well. And so those are our transforms. Number 6. here. So f is a piecewise defined function. We're going to find the values of f of 2 and f of negative 2. All right, for f of 2, 2 is bigger than or equal to negative 1, so it's going to follow the quadratic rule. I'm going to say f of 2 equals 2 squared minus 1, and that's going to equal 3. And then f of negative 2, since negative 2 is a number that's less than negative 1, I'm going to follow this rule, is equal to the negative of negative 2 minus 1. So I've got 2 minus 1 is 1. So those are the values of f of 2 and f of negative 2. We just have to know which rule to plug into based on the rules about the domain. Describe the behavior of f at x equals 1. Oh. Okay. If I plug in at oh, whoops, that's supposed to say x equals negative 1. I'm going to change that so it's more interesting. At x equals 1, the function's in the middle of doing its like parabola type behavior, and so that's not, you already knew that. Okay. X equals negative 1, that's a more interesting point. That's where the piecewise function is kind of like splitting. So I'm going to say, all right, at x equals 1, I'm going to just plug into the two pieces and see what happens. Negative of negative 1 minus 1, that would be equal to 0. And then negative 1 squared minus 1, that's also going to equal 0. So since they're approaching the same value, what's going to happen is I've got this negative sloped line, and until x equals negative, or until, yeah, as long as x is less than negative 1, so up to, but not where it's equal. But then it's x squared minus 1, where x is negative 1. So, and we determine that they kind of meet up there at 0. So it kind of looks like that if this is the y-axis and that is the x-axis. And so I'd say the function's continuous at x equals negative 1. Because the two pieces agree, okay, with the x value that they kind of share plugged in. Graph of f, oh, look at this. Lucky me. I've already got a graph of f, so that's going to be negative 1. That's going to be 1. This is also negative 1. I'm happy. That looks good to me. All right, yeah, that's the sketch of the graph of f. That was fortunate. Okay, I'll just label that part C, and I think I'm going to move on. Just 2. So with 7, we've got this absolute value function. And so I guess we could start with sketching the graph of y equals g of x. Negative 3 absolute value of x plus 8. It's been a long time since we've sketched one of these. We've sketched a lot of those in this class. So, and you know, just because it was a long time ago doesn't mean that you're just like free to forget about it. We need to be able to keep doing these things. So for A, negative 3 absolute value of x plus 8. Okay, well, negative 3 absolute value of x, regular absolute value of x makes a v. And so negative absolute value of x is going to make kind of an upside down v. But then I'm going up by 8, so I'm going to just label 8 here. And I'm just going to go down with a slope of negative 3. Or not, I guess that's a slope of 3. But I'm going downwards with slopes of 3, which in my mind are pretty steep, so I'm just going to draw it like that. Describe transforms of the graph of y equals absolute value x that would produce the graph of g. Now, this is a situation that I have intentionally avoided in this class, I'm realizing, where the order of the transform does matter. And I will say that I'm not going to mark you off points if you put them in the wrong order. I might tell you about it and be like, hey, this is kind of out of order here. But that's not the focus of our course, is these transforms that don't commute, what order they need to go in. That's not what we're talking about here. Okay, so if I was to describe the transforms of the graph of y equals absolute value x that would give the graph of g, I kind of need to start from the basic thing and say, okay, what happened to it first? Well, first it got multiplied by negative 3 in like a PEMDAS sense. So it's going to be a vertical stretch by 3. Okay. Then we're going to multiply by negative 1 on the outside, which is a vertical reflection, so it's a reflection across the x-axis. And then the plus 8 after that, well, that's just going to be going up by 8 units. Okay? So really, if you think about it, we had kind of a standard V. It got narrower, which is like it got vertically stretched, and then it went upside down, and then it went up by 8. Okay, so first, I mean, either of these two, because these are kind of the same type, they're both vertical, we can do those whatever we like. But then we need to do up by 8 after. But again, that's not really what we're focused on here. All right, C, find G inverse of 2. G inverse of 2 is G of x equaling 2. So I'm going to say -3 absolute value of x plus 8 equals 2. And then I'm going to just solve for x. And I know it's been a long time since we've solved a whole lot of absolute value equations, but if you needed to refresh yourself, you could just go back and watch one of those videos of me solving absolute value equations. That was something we kind of struggled with at the time, and I did a bunch of examples in the lesson, on the homework, on the quizzes, all of those things. So if you wanted to like kind of remind yourself of what you learned about in September, you could just go back and watch some of those videos. They're still there. So I'm going to subtract 8 from both sides, and I'll have -3 absolute value of x equaling -6. I might divide both sides by -3 and say absolute value of x is equal to 2. And, you know, we better hope this comes back positive, because if the absolute value of x equals a negative number, we say it has no solution. Okay? But that would be if we said that this thing was equal to like 10 or something up here where there's no graph. Okay? I wouldn't be able to pull back anything. So absolute value of x equals 2, that's where x is equal to 2 or -2. So I'm going to conclude that G inverse of 2 is the set that has -2 and 2 in it. Right. The graph of y equals b of x is formed by horizontally stretching the graph of g by a factor of 3. Right, write a formula for b of x. All right, well, remember that a horizontal stretch by a factor of, say, k, is where we're going to take x and we're going to replace it with 1 over k times x. Okay, so that's what I'm going to do in the formula for g to get to b. So b of x is going to equal g of, okay, we're horizontally stretching by a factor of 3. That'll be 1/3 x. And then wherever I see x in the formula for g, up here, I'm going to replace it with a 1/3 x. So it's going to be -3 absolute value of 1/3 x plus 8. And like, yes, you could simplify this factor out to 1/3 and make that negative absolute value of x plus 8, but you'd be no more right than I am right now. So I'm just going to stop there. Okay, and that's all for number 7. Just got one more on our way. So h of x is the log with base 10 of 2x. Again, with this log base 10, it must be, I must have been concerned about y'all's ability to evaluate logs with base 10. It must be one of those on the test. So if I've got h of 500, kind of like with composition of functions, when I'm plugging in 500, I'm going to just, wherever I see x in the formula, I'm going to replace it with 500. So that's log of 2 times 500 is 1,000. Okay? And when I don't see a base, I know it's implied 10. I say, what exponent do I put on 10 to get 1,000? That's going to be the 3 exponent. And then b, the graph of y equals c of x, is formed by reflecting the graph of h across the x-axis. And, you know, I don't think I've really pitched it to y'all like this in this class. But if you know, take something, I'm just going to do a point, and you reflect it across the x-axis, you end up with, you take y and you replace it with -y. So if I was going to do that to this, y equals log of 2x, I'm just going to replace it with -y, so it'll be negative log of 2x. So I'm going to say c of x equals the negative of h of x, and multiplied y by -1, and that's going to be negative log of 2x. Now, if you wanted to write that as an exponent and simplify it farther, this could be written as log base 10 of 1 over 2x, but that's not necessary, right? This is an equation, a formula that gives c of x, and so that's going to be good enough for us. And that's going to be all for this video. Okay, it was a nice short review. Hopefully you saw some things that you hadn't thought about in a while that seemed unfamiliar, because I don't want them to be unfamiliar too on the test. But if you're thinking you need more practice, which I think you probably do, you should go in and look at those quizzes, watch the video solutions for those, after trying them yourself. maybe looking at some homeworks, going back, looking at the notes, all that stuff. So that's going to be all for this video. Thanks for watching.